In this video, we want to look at how to field quadratic applications quickly and effectively using a graphing calculator. The example we're going to use is on the screen in front of you here. It's question 8, which is entitled Enclosing a Rectangular Field. When you read this question, it might seem familiar. You might think to yourself, I think I saw something like this in a previous course, like intermediate algebra or some equivalent. And you're probably right, because this is exactly the kind of question that I would ask in intermediate algebra, and I'm sure that many other instructors are likewise. The difference is that in this class, we require a graphing calculator, whereas when you took intermediate algebra or whatever equivalent, you may not have had access to a graphing calculator. And so we want to show you how you can put that graphing calculator to work in order to quickly and effectively answer this question. So what would you have to know in order to answer this? Well, let's dig in after we talk about some review here real briefly. You might remember that a quadratic function is of the form f of x equals ax squared plus bx plus c. That's the expanded form of a quadratic function. You can also say the same thing in another form, which we call the factored form, x minus r sub 1 quantity times the quantity x minus r sub 2. R sub 1 and r sub 2 are the roots in that case, and that factored form works even if the roots are complex. Now, you may remember that when you're looking at the expanded form, certain things can be read if you know how to read them. For example, a is the leading coefficient, and you might recall that when a is positive, in other words, when a is greater than 0, and shown in this graph here on the left, that the graph of the quadratic opens upward, as you see. And down here where the vertex is, the vertex represents a minimum value for the quadratic. Similarly, when the leading coefficient is negative, that is when a is less than 0, as you see here over on the right-hand graph, the vertex represents a maximum value for the function. Regarding the factored form, one thing that's helpful to remember is that the vertex is always halfway between the roots. And so if you know the locations of the roots, a very slick way to find the vertex is to just average the roots. And believe it or not, but that even works when you have complex roots. Now, let's see. If you were to look into many different quadratic examples and kind of, get the big picture, you would notice probably that they are asking the same questions over and over again. And if you tried to summarize those questions, you might come up with something like the following. So one question that's commonly asked is number 1, where they give you the quadratic model and they give you an input value, in this case x sub 1, and they are basically asking you to plug it into the function and produce the corresponding output value. You may also be asked to explain what it means in the context of the problem. Another common question is what you see in number 2, where you're given an output value, y, and you're asked to solve the quadratic equals that output value. So in other words, you're being asked to find the corresponding input value or values that produces y. Now, in a class like intermediate algebra, you would probably use a quadratic formula or possibly factoring to field that. But you can also use a graphing calculator if you know how to do it, and we'll show you, probably not exactly in this video for that particular question, but in a future one. And then regarding question 3, it says, what are the coordinates of the vertex of f of x? Well, that's another common question, but it's typically not asked in that way. It's usually asked in the context of the problem, where they ask for some maximum or minimum value depending on what the model is doing. And so if you go back to the question at hand here, number 8, it says enclosing a rectangular field. Beth has 3,000 feet of fencing available to enclose a rectangular field. Part A, express the area A of the rectangle as a function of x, where x is the length of the rectangle. Now you can't do this entire question on the graphing calculator. You have to do some thinking. And so that's going to come in part A right here. So what do you need to know in order to answer that? Well, you have to know that the perimeter of a rectangle is twice the length plus twice the width. That's one way to put it. You could also factor out the 2 if you wished. And you can also express the area as a function of length and width. It's length times width. Now in this particular case, you can go back and read the question and see this. They're asking for what value of x is the area largest, what is the maximum area, and so on. And so they tell us also that the woman has 3,000 feet of fence, and so if she's trying to enclose the largest possible area, I think it's a safe assumption she's going to use all of the fence. And they also tell us to use x for the length. And so if you think about, well, what do I need to do? You need to isolate the width because we know the length is x, and we need to find the area as a function of x. And so you can start with the perimeter equation here. And if you subtract 2L from both sides, you would have this expression here. And then you could isolate W by dividing both sides by 2, as you see. And if you then plug in 3000 for P and simplify the expression, you obtain what we have down here, which is 1500 minus x for the width of the rectangle. And so if you put everything into a picture, x being the length, 1500 minus x being the width, it's clear that the area, which is length times width, is going to be a function of x, and it's going to be x times a quantity 1500 minus x. And so that is the function that we need to put into the graphing calculator. It's also the answer to part A. Now, as far as using the graphing calculator, it's a graphing calculator, so if you can't see the graph, then you're not going to have much utility from it in this particular case. So if you wanted to graph a function like this, you go to the y equals memory register here and key it in. X times a quantity 1500 minus x. And you could then try to graph it. Now in this case you can see the window size. This is the standard zoom, so you go -10 to 10 on both axes. And it's not a particularly useful picture because it looks like you have a vertical line here. It's not actually vertical, but it looks that way. And so clearly we need to fine-tune the window size because, you know, the reality is when you're using the graphing calculator, if you can't see the answer on the screen, meaning if you can't see it on the graph, chances are the calculator is going to have a hard time finding it for you. So one thing you might want to try would be what we call zoom fit. I've showed you in a previous video that sometimes zoom fit works, sometimes it doesn't. This is one of those cases where it doesn't work, at least not on this calculator. So if you were to go to the zoom menu and you can scroll down here, zoom fit is 0, right? Function number 10, if you will. And so to select it, you can press enter, or you can just press 0. And so you can see that it does change the appearance of the graph slightly. If you go back to the window, you can see how. Basically what it did in this case is it changed the y values. But again, the graph isn't very helpful because, well, we can't see what we need. We're looking for a vertex, as you'll see, and I can't see it. So I need to fine-tune the window a little bit more. And if you go back and look at our function, the function can actually inform your efforts here. So you can see by inspection when you look at this, if you were to set a of x equal to 0, you'd have a 0 at x is 0, and you'd have another at x is 1500. And so both of those would be something you'd want to see in the graph. And so the window size has to accommodate that. And then as far as the vertex is concerned, well, we'll figure that out. So for x minimum, I'd probably start at 0. For x maximum, you could go up to 1500 if you want it, but I'm going to go a little bit further. And as far as the x scale is concerned, again, this is the distance between the hash marks on the x-axis. So you can pick whatever value seems good to you. You could use 100 or 200 or 500 or 1000 or whatever. I'm going to use 100. And as far as the y values are concerned, the area can't be negative, so there's no need for any negative y values. And as far as y maximum, you know, clearly 14,900 wasn't working for the previous, you know, when we looked at it before. So I'm just going to take a wild guess and put like 1,000,000, something like that. And if that works, great, and if it doesn't, then we'll fix it. As far as the y scale, if your y-axis covering 1,000,000 units there, you probably want a scale of 100,000 or 200,000 or 500,000, something like that. I'll just go with 100,000. And these other values down here, xres, delta x, trace step, don't touch those. There's no reason for it. Here's my graph. And that's not a bad view, but, you know, I'm looking and I have a little bit of wasted real estate up here, and it looks like it's flat through that whole portion right there, which is deceptive. So I think I need to kind of zoom in a little bit, and I'm looking here, and it's 100,000, 200,000, 300, 400, 500, 600,000, and that definitely looks like it's above the vertex. So I'm thinking, yeah, let's change the window a little bit. instead of going up to 1,000,000, let's go to 600,000. And let's look at it again. That's a much nicer view. So regarding our question here, let's make sure we're staying on track. Part A was asking for the area as a function of x. And so again, we gave that to you. It was right here. We said that a of x is x times the quantity 1500 minus x. Part B is asking for what value of x is the largest, or is the area largest? And part C is asking what is the maximum area? Now, collectively, parts B and C are both asking for some part of the vertex. So B is asking for the x coordinate of the vertex, and C is asking for the a of x coordinate of the vertex. And the calculator can give those to you. You could use what you know. I mean, it definitely can help to inform what's going to happen here. Let me show you. You may recall that the trace function is a poor choice for locating the vertex because the precision of the trace function is dependent on the window size. And so you might look at it there and say, well, it looks like my vertex is at 751.51 and so on. But you know, if you put that into MyLab, you're going to get marked wrong on that because it's close, but it's not on the money. And so we need to have a better answer. And so what we've suggested in previous videos is that you would use either the minimum or the maximum function, and that's what I'm going to use here is number 4. So as far as a left bound, I'll go with 700, and as far as a right bound, I'll go with 800. And as far as a guess, I'll put in what the calculator had through the trace function, which was 751. And you can see what the calculator coughs up. Now, you can see from inspection, once this sort of is revealed here, that the vertex is actually at 750. It's not hard to see. You can go back to what we were talking about. And as we said, this function has a root at 0 and a root at 1500. And the vertex is always halfway between those. And so if you were to average those two roots, that's where the vertex is. Take a look. So you can say 0 plus 1500. And that's one way of finding the vertex. The other would be to use the vertex formula, which would be minus b divided by 2 times a. And so in this case, you have to expand a of x. But if you do, you can see that b turns out to be 1500, and a, the leading coefficient, is -1. And so if you were to evaluate that formula, you get the same thing, -1500 divided by the quantity 2 times -1. And the reason we want you to know that is because you have to understand that when you use an electronic device like a graphing calculator to find something like a maximum value, and it looks like it's still on the screen there, but well, it's the traced value. We need to have the precise one. So I'll go back and do that. Yeah, sorry. We had said 700 and 800. And then let's put in 751 as we did previously. You can see that we're in the ballpark. And so even though the question does not have any particular instructions about rounding, I would be entirely comfortable submitting as an answer for this 750 for x. Now, how would you know that if you hadn't gone through the steps of finding the vertex in the old-fashioned way? Well, you know, think about it on a practical level. If you're measuring out 749.99998 feet of fence, that's a tough measurement to have so exact. So I'm thinking that, you know, it'd be very easy to make a case for rounding that to 750. And by the way, that is the answer to part B. I would definitely round it in this case because the integer value is so large compared to the fractional portion, and so it makes perfect sense to round it. Why doesn't the calculator give us the exact the exact answer? 750? Well, again, there's round-off error involved when you use an electronic device to find maximum or minimum values, and in this case, we're experiencing some of that. Now, this other value over here, the y value, this is the maximum area, and this is the answer to part C. And so here's your answer to part B right here, 750. Here's your answer to part C right here, 562,500. And if you put those both into MyLab, I'm sure you'd have no problem. Now, if you keyed in 749.99998 into MyLab, how would it respond? Yeah, it's a good question. It's definitely within the tolerance for the answer, so it would probably mark it correct. I'm very confident that it would. of course, we'd prefer 750. Now, as far as putting the answer in written form, we showed you that there are several ways to find the vertex. The most important thing about Part B is recognizing what they're asking for, which in this case is the x-coordinate of the vertex. And likewise, Part C, they're asking for the a of x coordinate, and you can find it a couple of ways. We just showed you one on the graphing calculator. I hope this has been helpful, and if you have any questions, please feel free to drop me a line. I'll show you that second question, which if you recall is right here, solve f of x equals y using the graphing calculator. I'll show that in a future video, so be on the lookout for that.